Alright, so in this particular video, we have an object that is launched from an initial height 50 meters above ocean water here, sea level. And it wants us to do A, B, C, D, E, and F. Let's get cracking. Alright, so the first thing I like to point out is that because it's being projected upward, as the ball rises, its velocity vector decreases. It gets shorter and shorter because the object is slowing down. Eventually, at some point, when it reaches maximum height, it's going to stop, change direction, and come back down. So here, what on the screen that's coming up here, these are your velocity vectors, and then as it passes the initial position, it keeps falling an additional 50 meters. So the velocity vector has to keep getting faster and faster. Okay. All right, let's do part A. Part A wants us to find the maximum height relative to the ocean. So what I want to do is I want to find the height from where it was launched all the way to where it stops, and then add the 50 because it says relative to the sea. Okay. So here I'm just going to use this kinematics function that's time independent. I'm using this because Vf at the top of the trajectory is 0, so I'm going to cross that out. I know my initial velocity here is 24 because the diagram said so. All right, and I know what g is. G is given to us as negative 9.8 meters per second square here on Earth. So other than that, I'm just going to go ahead and cross out Vf square. And then I'm going to simplify this function, and then I'm just going to go ahead and do algebra and isolate for delta y, because ultimately I want to find delta y. Watch my cursor from where it was launched all the way to the where it stops, and then once I find that, I can just use common sense and add the 50, and that'll be my answer. Okay. So to get delta y by itself, I just divide both sides by 2 and g. So here we know everything already. Once again, vi in the diagram is 24. I'm going to square that, and then g is negative 9.8. I'm going to just plug that in. And then the negative sign here on top and bottom will naturally cancel out. So if you do calculate correctly, 24 squared will give you 576, and then 2 times 9.8 is 19.6. And then once again, the negative sign cancels out, and this will give you a height of 29.4. Okay, so while this function solves for the displacement, really here the question asks for height, so I don't really care for direction. So it went up 29.4 meters before it changes direction and falls back down. Okay. But that's not our answer, right? What I just found here is just the height from where it was launched. But the question here is asking relative to the sea. So you got to make sure you read. So here, I want to take the 29.4 and I want to add it to the 50 meters because the ball was initially 50 meters above sea. All right. So my final answer is going to be 79.4 meters. That's that. Okay. Now, if you want to, you can do this. You can use your displacement function. You can find delta y from where it was launched, right, to where it stops, and then add it to it. So to find displacement, I need VIT plus 1 half GT squared. VI is given as 24. I don't know how much time it takes to come to the peak, right? The problem didn't tell us the time. It just told us the initial speed. Here, G is negative 9.8. So as you can see, I have T's here that are unknown, but that's okay. Well, to find delta Y, I need T's. Well, I can use information given in the diagram. Well, I can use acceleration as Vf minus Vi divided by t. So here g is acceleration due to gravity, but to find time, I can just switch these two. I would just move t up to the top left and then move g down to the bottom right, or multiply both sides by t at the same time, divide both sides by g. That will give you the same thing. Okay. So here in my work, I highlighted t here because this is what I need, right? To find delta y, I know my vi, I know acceleration due to gravity. The only thing I need is the variable t. So doing this strategy here allows you to find t. Well, what's your VF? Your VF is going to equal to 0 because from launch is 24 meters per second. It's going to rise at the peak. It stops, so VF has to be equal to 0. So VI here, I plug in 24, and then the acceleration due to gravity is negative 9.8. Once again, the negative signs here naturally will cancel out because time is a scalar. So if you do this correctly on your calculator, you get 2.45 seconds. Now, once I know t, I can just plug it back in, right? I can just carry my work down. So here, the displacement function just get carried down, except wherever t that was highlighted in yellow, I'm just going to plug in 2.45 seconds because that's what it is. And if you simplify this on your calculator, you get the same magnitude, which is 29.4 meters. Keep in mind, the 29.4 meters is just how high it rose from its initial position. But this question in part A asks relative to the height. So once you find 29.4, don't forget to add the 50 based on the wording for this particular part. Okay, that's that. Let's move on. Okay. Part B wants you to find the time that it takes the ball to reach maximum height. So by doing the second strategy, we actually already found the time to be 2.45 seconds. Okay. So usually, you can crack these parts out in one strategy. If you like, you can use a couple different strategies by doing so. You sometimes find answers to other parts. So the answer to part B here is just 2.45 seconds. However, what if you just did part A, right, using the left strategy, and you didn't need to touch time? How do you find time from scratch? Well, to find time from scratch, I can just use my average velocity functions, right? Average velocity by definition is displacement over time, but under constant acceleration, which it is for this one. You can do VI plus VF divided by 2. Well, what's my VF? My VF is going to be 0. I'm trying to find time, right? I'm still on part B. It's green here. I'm trying to find time, but you notice here time is in the denominator. So what I'm going to do is I'm just going to be clever. I'm just going to flip the function up on its head so that I can get t in the numerator. So therefore, I can just say change in time over change in y is equal to 2 divided by VI. And from here, to find t, multiply both sides by delta y. So I'm just going to do that really quick. And it's just plug and chuck, really, right? The 2 is part of the function. And then VI is 24. And then what's your displacement? 29.4, because we already found that in part A. So if you simplify this, you'll get 2.45 seconds as well. Okay. Now, if you want, okay, you can also use your displacement function. Why? Because it has a t in it. Okay. However, what I want to do is I want to teach you to just be more clever. You can actually start the problem from peak. So we know that it comes to a stop at the very peak and it's going to fall back down, right? Well, why do I want to start from peak? If I start from the peak, I can say that my initial velocity is 0 because it has to stop before it, comes back down. So if I reference the peak, my VI at that point is 0. So from here, we can just crack out all this basic math. Well, what's your delta y? Delta y here is going to be negative 29.4 due to symmetry. We already found in part A that it went up is 29.4 meters. So therefore, if I start from the top and I go all the way back down to here, that's just negative 29.4 because it's just moving downward, and displacement is a vector, so you make sure you include the negative sign. So on the right side, g is just negative 9.8 meters per second square, and really, as you can see here, the only thing we're missing here is just t, or t squared. So simplify this down. 1/2 times negative 9.8 is negative 4.9. So to get t squared by itself, divide both sides by negative 4.9. That's what I did on my work here. You simplify the left side, it gives you 6. But this is t squared, so to get t by itself, you need to take the square root of both sides. Therefore, the square root of 6 is just 2.45 seconds. So there you go. You've seen 3 different strategies now, which allows you to find t on the way up, right, to be 2.45 seconds, right? Watch my cursor. The time up is 2.45. Therefore, the time coming back down to the same spot must also be the same 2.45 seconds. So you can start anywhere you want. Just be consistent with values that you apply in these kinematics equations. Okay. All right, let's do C. C asks you to determine the time it takes to hit the C. Well, I'm just going to use my displacement function. Why? Because I know a bunch of stuff already, right? Well, what's my delta y? The ball started at the height here, but it went up and then it changed direction. It came down, but it continues to fall into the sea. So if you think about it, displacement is just a straight line from start to finish. So here's the ball where my cursor is. Yeah, it went up and all that good stuff, but I don't really care, right? Displacement is independent of your path taken. So all I really care about is where did it start, which is from here where my cursor is, and where did it stop, or where did it end? It ended in the sea. So my cursor just traced down 50 meters, but its displacement, so it's negative because you're falling, you're 50 meters below where you started, right? So here in my work, delta y must be negative. I highlighted here because it's essential that you put the direction there. Otherwise, you're gonna goof on just algebra work. Okay. Well, what's my VI? My VI is positive because it's being projected upward. Once again, g here is just replaced with negative 9.8. So as you can see, you have t and t squared. So here, it's pretty light work. I'm just going to simplify 1/2 of negative 9.8 to negative 4.9. And then as you can see, hopefully your math skill comes in here. You have a t squared, you have a t, and then you have some coefficient. You need to recognize that this is just a quadratic function. So I clean it up for you with all the units. I'm going to put negative 4.9 t squared first. And I'm going to put 24t because this is how we will properly write it in math, with the highest exponent term first, right? So it'll be negative 4.9t squared plus 24t. And then this negative 50 on the left side needs to be brought over because you need to set the function equal to 0 so you can find roots. So negative 50 will turn into positive 50. So once you have this, I'm just going to go ahead and tell you to do quadratic solver on your calculator or on a computer. So I'm not going to waste my time doing it here for you. But so if you don't know quadratic, learn how to use it on your calculator. Okay. So here I just need to identify what A is. A is negative 4.9, B is 24, and then C here is a positive 50. And if you do that correctly using a quadratic solver, you'll get 6.47 seconds, and that is the time for the whole entire motion. Okay. Now, if you don't want to do that, right, you can just break it up. We already know the time from start to peak was 2.45 seconds that we calculated. Well, what I can do now is I can actually start from peak all the way down to the C. Okay. Well, why do I want to start from peak down to the C? Well, if I start at the peak, I can find the time that it takes to follow this whole entire right side and just add it with the time on the left side that I already calculated. So if I do this correctly, okay, my VI is going to be 0 because I'm starting at the peak. Well, what's my delta Y? It's important that you plug in the right delta Y here, because delta Y here is not negative 50. It's actually negative 79.4 because, well, watch my cursor. If you went up here, that's already 50. You found the maximum height, which is 29.4. So therefore, to go from peak back down, this is 29.4 plus an additional 50. So that'll give you 79.4. But again, if I start at the peak, it's moving downward. So delta Y is a vector. So you need to put the negative sign. All right, other than that, if I start at the peak, VI is 0. And then G, once again, is just plug in for negative 9.8. Here, the only thing left unknown is T squared. So if you simplify stuff correctly, 1/2 times negative 9.8 is negative 4.9. To get T squared by itself, divide both sides by negative 4.9. So if you simplify 79.4 divided by 4.9, you get 16.2. And then you still got to square root that because you need to find just T. The square root of 16.2 gives you about 4.02 seconds. But again, this is not your answer, right? This is just the time to fall down, right? So you found the time to fall down from peak all the way to the C. All you have to do is add the time on the way up. So here in my work, I put T total, which is the time going up, which is 2.45 seconds, and then the time coming down, which is 4.02, and it gives you about the same answer. Okay. Let's do part D. Part D wants you to find the velocity when it hits the C. I think the quickest way is just you want to use this common form, which is time independent. So here, to find VF, I'm just going to move VI to the other side, so it becomes a plus. And here, really, it's just plug and chug, right? G is given. What's your delta Y? Delta Y is negative 50 because I'm looking at the whole entire motion. It's 50 below where it started. What's my VI? 24. And don't forget to square these terms to what are appropriate. All right. So if you clean this up, you'll get 1556. Therefore, to get VF by itself, take the square root of that. And then the square root of 1556 will give you a positive or a negative number. Don't forget, when you take the square root of a number, you get two answers, a positive or a negative. So it'll be positive or negative 39.45. And in this case, I would choose to go with the negative answer because, well, it's on its way down. It's that easy. Okay, so make sure you're careful with how you present your answer based on how questions are asked. So it says here the velocity. Because velocity is a vector, I need to pick the answer that's appropriate. And negative is the answer for this one. All right, there you go. Now, if you don't want to do that, you can just use VF is equal to AT plus VI. So here, I need to find VF, but I can just go from peak to C. Okay, why do I want to start at the peak? Well, again, VI is equal to 0. So as you practice, you just have to learn where should you start your problems just to minimize the amount of work. So here, G is negative 9.8. And what time do I plug in? Well, I just need to plug in 4.02 seconds because in the previous slide, I found the time that it takes to fall from the peak all the way down to sea level is 4.02 seconds. So if I start at the peak and go down to sea level, the time must be the same, 4.02. And if you do that, you'll get the same answer, which is negative 39.4 meters per second. Okay, and there's that. Now, if you want, you can do the whole entire motion. You can use the same function for the whole entire motion, right? So here, if you do that, G's hasn't changed, negative 9.8. Well, what's my time? The time for the whole entire motion, as we figured out in the previous slide, was 6.47 seconds. Well, what's my VI then if I look at the whole entire motion? Well, if you look at the whole entire motion, it started off being shot upward with the speed of 24 meters per second. So VI needs to be 24. And then other than that, if you simplify this down, you'll get the same answer. Okay, so you'll get negative 39.4. So there are three different strategies here. You figure out what works for you. I personally like the peak to see if you know the time, which we did for this one. If not, then just do the left strategy because I think it'll just be safe and it will work out. Okay, just be careful with your signs because if you don't put in the displacement correctly as negative 50 here, when you sum this stuff up, it will mess up your answer. So be careful with signs. Displacement is a vector. Okay. All right, let's do E. The do E, calculate the average velocity between 1.4 to 3.3 seconds. That's pretty light work. So to do average speed, there's a couple different strategies. Here, I'll show you this one. You can just find the speed at the two different times and just add them and then divide them by 2. Okay. So here, I'm just going to find, even though it says VI and VF, VI here is actually at 1.4 seconds, and then VF takes place at 3.3 seconds. So I just need to find the two V's at these two times. So here is the velocity at 1.4 seconds. So velocity is just G times time plus VI. So if you plug stuff in, you get 10.28, and you would do the same again for 3.3. The only thing different here is just plugging in the time. Okay. So if you do that, the velocity is negative 8.34 at 3.3 seconds because it's on its way back down. So all we have to do is add these two values up. So 10.28 plus negative 8.34 divided by 2, and you'll get positive 0.97 meters per second. And I include the positive sign here because it says average velocity, which is a vector. Okay. All right. Now, if you don't like that, you can do this, right? You can say, well, average velocity by definition is displacement over time. Well, look at the screen, right? I know what the time is. It went from 1.4 to 3.3, so the interval here is just 1.9 seconds, right? So 3.3 minus 1.4 is just 1.9 seconds. Well, I know the bottom, I know the denominator, so I know my change in time here is 1.9 seconds. But what's my displacement during that time? Well, I can just find displacement real quick. Well, I can use the displacement function. Displacement is VIT plus 1/2 GT squared. However, it's important, once again, you plug in values accordingly based on where the problem starts, right? So here VI is actually 10.28 because I found it here. The velocity at 1.4 is 10.28. Do not plug in 24 because 24 occurs at times equal to 0. But this problem here starts at 1.4 seconds. So make sure you pay attention to these conditions. All right, so VI here is 10.28. Well, how much time? 1.9, because the difference in 3.3 to 1.4 is 1.9. And that's it. Really, it's just plug and chuck here, right? So if you simplify all this, you get a displacement of about 1.843. Well, like I said earlier, if you apply the strategy, you need displacement over time. But time is easy to find because we just found it 3.3 minus 1.4, which is 1.9. So the only thing I was holding us back was the displacement. Well, now that we found displacement, we can just plug it in. 1.843 divided by 1.9 will give you 0.97. And again, the sign is just there just out of technicality because average velocity is a vector. And they didn't use the word magnitude, okay? All right, let's do part F. Part F asks you to find average velocity for the whole entire motion. I think this one's the easiest one out of all these parts. Well, average velocity, I'm just going to use this strategy because everything's given to me. Well, I mean, delta y was given initially, but time we already calculated. So what's my delta y? Negative 50. Again, it's negative because it's below where it started. And then what's my total time? Well, we already calculated, so we need to rewind the video. The total time is 6.47 seconds, okay? Because it took about 2.45 seconds to rise, and then it took about 4.02 seconds to fall all the way back down. So that's where the 6.47 comes from. And if you do this correctly, you get negative 7.73 meters per second. And the answer is negative here because, well, just using common sense, you're below where you started, so the average is going to be negative. Okay? All right. That's it for this video. I hope that helps. Listen to again if you need to, and hopefully learn there are different ways to solve these parts. Good luck. Stay nerdy. Don't be whack.